Okay. So 1.9 is going to be sort of an interesting deal that we're going to take out of it what we need and nothing more. So if you flip to where it says 1.9 in your book, you'll be greeted with the following title. 1.9. Continuity of a composite function and continuity on an interval. Well, deal is that we're not actually going to concern ourselves all that much or at all. Well, that's not true. We will concern ourselves just the bare minimum amount on these two topics. And really what we're going to pull out of section 1.9 isn't even in the title. They just kind of tuck it away deep in the lesson. But we're going to add it as a parenthetical or an A positive. Was that this class that came out? A positive. And the intermediate value theorem. And really, it's this last guy, the intermediate value theorem, that will be the focus, at least our focus, for this section. No, I think it's good off. You guys all see your own notes? Okay. Oh, good. So the intermediate value theorem has two conditions. We're not going to tell you what the theorem is just yet. I'm going to tell you one of the conditions because that's going to motivate our brief discussion of what it means to have continuity on an interval. And one of those conditions is that you are continuous on a closed interval, that a function is continuous on a closed interval, brackets, closed. Well, let's recall, in 1.8, did we talk about continuity on intervals specifically? No, you don't remember? Let's go back to what the title is. Continuity of a function. Where? At a number. Is a number an interval? No. Numbers are in intervals. We didn't really figure out, okay, how do we extend this? We were given these three little i's, and this was for testing individual numbers. Is our function continuous at 8? Is our function continuous at -12? At single numbers, which is good as far as it goes, but oftentimes we want to be able to say about larger swaths of area than just one number, and that's where intervals come in. And specifically with the intermediate value theorem, we want to be able to say that something on a closed interval is continuous. And so we're going to kind of briefly look into what that means and why it could be an issue. So recall, in section 1.8, we examined continuity of functions at specific numbers. That was the three little i's. Does the function exist there? Does the limit exist there? Are those two things the same? Hopefully after 1.8, we're feeling pretty familiar with the three little lines. But what happens when we want to discuss continuity on an interval? And specifically, we're going to start with talking about continuity on open intervals. Question. What happens if we wish to establish continuity on an open interval? No. The answer, not very exciting, but it's a definition. The definition of continuity on an open interval. And this is kind of sort of intuitive, like it kind of just makes sense what we're about to write down. But in practice, we need to kind of know what it's going to look like. But a function is said to be continuous on an open interval if and only if it is continuous at every number on that interval. Continuous at every number in the open interval. Which sounds like kind of a lot of work. Like, how do we have to show every single number on some interval? That's kind of an impossible task because an interval has an infinite number of numbers within it. Like, how do we know that that is continuous at every single number? So practically speaking, what this means is just relying on what we know about certain functions to say that this is true. What's a number that we know is going to be continuous out of a lot of numbers? Or what type of function? Polynomials. Anytime you have a polynomial, you can just name an open interval and say, hey, this is a polynomial. I know that it's continuous on this open function. For rational functions, if that interval is part of its domain, you're good. For radical functions, same. If you're in the domain, you're continuous on that open interval. So practically speaking, continuity on open intervals can be assumed for intervals included in domain of function. And that's a little bit loose there because obviously we can have intervals that are part of the domain, but there might be some weird limits going on. But by and large, if we're talking about continuity on an interval, we're going to say something like, oh, it's a polynomial. It's continuous on that interval. The issue that we're going to kind of skirt around, but that we're really trying to get to, that we're going to need for one of our conditions on the intermediate value theorem, is what about a closed interval? And closing an interval requires us to answer what is the continuity of the endpoints, which might not seem like a big deal, but we're going to do an illustration to show why it is, and then briefly talk about the workaround, and then finally get into the IVT. So open interval, cool. It's continuous at every number on that interval. Because it's open, doesn't include the endpoints. So you can prove continuity on every point. Endpoints, we'll see. So what happens if we want to close an open interval? To go from continuity on the open interval from A to B to the closed interval from A to B. Well, let's do an illustration to show why this could be an issue. If you're dealing with an easy function like a polynomial, this is sort of a matter of fact that, okay, yeah, obviously it's continuous on that open interval, and we can close it because we know that it's continuous at every number, including A and B. But sometimes it's not quite that straightforward, which we'll see in illustration 1. Let's consider f of x is the square root of 4 minus x squared. What's the domain of this function? We need positive numbers under the square root. So it's not all positive numbers because we need a specific value here. 4 minus x squared needs to be positive. So let's just write it out. So domain need 4 minus x squared greater than or equal to 0. Meaning we need x squared less than or equal to 4. Squared on both sides. What's the square root of x squared? Somebody impress me? Nope. Absolute value of x. There we go. Absolute value of x. If you had just said x, you would have ended up with x is less than or equal to 2. That is not a solution to this inequality because you can have -7 is less than or equal to 2. Does -7 fit into this domain? Okay, this is actually kind of important that we see this. If we had just said that the square root of x squared was x, and we just ended up with the square root of x is less than 2. Is -7 less than 2? So according to our shoddy math, is that a solution to this equation for this inequality? When you plug in -7 here, you get 4 minus 49. Is 4 minus 49 greater than or equal to 0? No, this is not correct. This is the correct next step. This leads us to the correct domain that we need x to be sandwiched in between, yes, less than or equal to 2, but also greater than or equal to -2. Square root of x squared is the absolute value of x. And so our domain is this guy, which is a closed interval. However, at this point, we can only for sure say that we are continuous on the open interval within that domain. So from -2 to +2. question is, what about these endpoints? So what about continuity of endpoints? Because we can show that -2 and 2, that our function is continuous there, then we can close those parentheses. So just for example, we could use 2 just as well. What happens at x equals -2? Oh, let's draw a quick graph here of this function. This is, of course, a semicircle. Of radius 2. Did I yell at you guys about numbering and labeling your graphs? Number and label, or use a straight edge and label your graphs, please. And then our graph looks kind of like that. So if we want to know about the continuity at x equals 2, we run it through the 3 little i's. So first little I. Does the function exist at the number we're looking at the continuity of? Sure do. Plug in a 2 there. 4 minus 4 is 0. Square root of 0. That's 0. So far, so good. How about the second little I? What is the limit of f of x as x approaches -2? Well, this usually requires us to go left and right limits and see that they match. Let's start from the right. Limit of f of x as x approaches -2 from the right. What does this function appear to be as we come from the right of -2? Yeah, looks like it's going to 0. So far, so good. But then, is there a limit from the left of -2? What is my, where does my finger go? I don't, there's no curve, there's no function. There is no limit from the left. Which means the limit at -2 does not exist. So according to our current definition of continuity, is our function continuous at -2? No, because it just kind of falls off into the abyss. And there's no way to establish that limit. So the limit at 2 does not exist. Sorry, -2. Therefore, not continuous at x equals -2. It just doesn't really sit right with us. We kind of look at it like we can tell, at least from the right, it wants to be what it is. It's not our fault that the function just stops there. And so what happens here is what happens more often in math than you realize, which is we have sort of an issue with a rigid definition, and we sort of just redefine that definition to fit our needs. You know, the most obvious example is like the integers. For a long time, man just had whole numbers, and really just natural numbers, scratches on the wall. 1, 2, 3, 4, 5. I've got that many pellets. I'm a caveman. But then at some point in our development, we realized, I know the definition of numbers is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. However many pellets you can scratch on that wall. Pretty nice to be able to say that I owe somebody some pellets. And what do they come up with? Negative numbers. Okay. And this is sort of analogous to that. Analogous. Is it a G or is it a J? Analogous. What's an analogy? Not an analogy. See what I'm saying? Why is it an analogous? Now I'm confusing myself. Whatever. It kind of matches this situation where our definition of continuity wasn't quite inclusive enough. And so we're going to expand it to include right and left-handed continuity. So the solution here is kind of a cheap workaround, but we do a lot of cheap workarounds in math to allow us to say things that we need to say. I need to be able to express the fact that I owe you a certain amount of money. Oh, there's negative numbers. I need to be able to express that even though we can't prove the left-sided limit matches the right-sided limit, that this thing is continuous on this interval. And so the solution that we're not going to spend much of any time actually working with is that, so how do we close? Use left and right-handed continuity, which essentially boils down to showing that the function value matches the right or left-handed limit at those endpoints. And for your purposes, the point is we can close open intervals. We can close open intervals. So why do we care? We can close open intervals. You might again be asking, well, why do we care about that? Why care? Need continuity on a closed interval for IVT. What's IVT? Good question and answer session. Well, now we can talk about the IVT. See, there we go. That was all just build up for the actual thing we're doing today. Here's the IVT. The intermediate value theorem. This is 1.9.8 in your book. The intermediate value theorem. And I like this theorem. I think you'll like it too. It's pretty intuitive. It sort of just makes sense. Involves some pictures. It's just a grand old time. Here's what it says. Now we're going to give you the straight out Lighthold version first, and then we'll kind of translate it into Smith sort of informal language, and we'll see some pictures. And we'll probably do a quick smoke break and do some examples with it. So we are now nearer to the end than when we first began, I think. We'll see though. If the function f is continuous on the closed interval, that's why we just had that little discussion. That wasn't much of a discussion, Mr. Smith. You kind of just talked at us. Yep. On the closed interval A to B. That's condition 1 of the intermediate value theorem. You have to have a continuous function on the given interval. And this is sort of part of condition 1, that f of A is not equal to f of B. Then here's the second condition. It's kind of hidden, so I'll tease it out as we go. There, not then. Then for any number k between those two values, which two values? F of A and F of B. Okay. There exists a corresponding number C in the interval A to B such that f of C gives you K. What does that mean? So if the function f is continuous on the closed interval A to B, and if K is chosen to be between the function values f of A and f of B, then there exists a number on that interval that's going to produce that K value.
What's after A?
Such that ST, sorry, shorthand. I'll say that again. You've got an interval, we'll draw a picture in a second. You've got some function values for that interval. If you choose a number in between the starting value and the ending value, and choose a number K in between there, there's got to be some number in between A and B that's going to hit K. So if you have a continuous function, it guarantees that you're going to hit all the values between the endpoints. And that's kind of my poor man's way of explaining IVT, is that should work precise here. That a function will hit words. Will hit every value between f of A and f of B. If the function is continuous. And that's, kind of what continuity is, that there's no gaps. You hit every value. So let's look at this graphically. I think graphically starts to kind of demonstrate exactly what's going on here. So definitely try to get it down neatly. That wasn't very straight, a little curvy. Looks better. Choose blue. We're going to do two graphs side by side, so leave some space. Doesn't really matter how big you make them. Oh, that was a little bit. Oh well. Okay. And let's just draw our curve to look kind of cubic-y. Something like that. And so we can choose some interval along the x-axis that we'll call A to B. There's an interval. Now, there should be corresponding function values. That's a function, that's what functions do. You give it A, it gives you f of A. Or if you give it B, it gives you f of B. So here is what IVT promises. Because we have the guarantee of the continuity of our function between f of A and f of B, we're going to hit every single value. Every single one of these values between f of A and f of B has to be visited in one way or the other by the time we get to B on the x-axis. And so if we choose some value k, and if k is indeed between f of A and f of B, and notice that k determines C, not the other way around. K is chosen first. We know that because this is between those two values, there's got to be somewhere on this interval that will produce this value. And graphically, we can see it. That if we go backwards here, check it out. There is indeed a number C that lies between A and B, such that we produce K. K is f of C. Got to hit every value in between f of A and f of B on your way between A and B. What I want to point out real quick are two kind of possible misconceptions here. Here's what it does not say. Does not promise two things. C is unique. It also importantly does not promise that f of C is sandwiched between f of A and f of B for all C in that interval, which seems like, wait, doesn't it say that? No. It says that if you've got a k value in between their function values, there's going to be a C that gives it to you. But you do not necessarily need all of your function values to fall between A and B. What's the difference? Picture time. A picture to illustrate both of these things.
What's the symbol to the right of C?
Included in, if C is in that interval. Okay, so let's draw a slightly more curvy graph here. Something like this. And if now we've got A here and B here, let's see what this picture looks like. We've got A hitting our graph there. And so here is F of A. And is this going to work? Yeah, that'll be fine. Here is F of B. A little bit wider, but oh well. Bless you. This is clearly a continuous function. There's no jumps or holes or anything. And so IVT will hold that if we choose some K value in between F of A and F of B, there's K. There's K. Somewhere in this interval from A to B, you're going to get a number whose function value is K. And actually, we can see that there's like 3 of them. So this helps to sort of illustrate the first point. These C values are not necessarily unique. There could be more than one C on that interval that gives you the desired K. In this case, there's 3. Also, so that was number 1. That's proof of 1. F of C sub 1 is equal to F of C sub 2 is equal to F of C sub 3, all equal to K. The other thing that is not promised by the intermediate value theorem, it does not say that if you choose a point at random in that interval, that your function value will be between the function values of the endpoints. And we can see this clearly, or you should be able to see it clearly. Let's pick this guy right here. We'll call it D. Do you agree that D falls in the interval between A and B? Let's see where its function value lies. Is F of D between F of A and F of B? No. So it doesn't say that, oh yeah, all of your function values are sandwiched between these points. It just promises that you can't get from A to B without hitting all of those points. You can go out and come back in. It just promises that you will hit every point in this little gap. I know it seems like a minor detail, but I think we get in our brain sometimes that idea. Kate.
Isn't C determined by K though, and K will always be?
Yes, so if K is chosen appropriately, we're golden. But what often happens when we're learning this is that we assume that the reverse is true. That if you choose choose a C, that it'll give you a function value that sandwiches in between those two things. So that's kind of maybe a good way to put it is K is chosen first and it determines C. C does not in any way guarantee that you'll have a value in between A and B. Sorry, f of A and f of B. And we'll see a couple of examples of this and the direction that it goes. If we choose K and then determine C. We're going to go live again at 11:30 with our last two examples. You got 5 minutes to smoke them if you got them, or have a snack, or take your phones out, or whatever you need to do. Go to the bathroom, cry silently to yourselves. I don't care. Oh, Zoomer. No, I'm not going to stop the recording because I'll forget to turn it back on. You have 5 minute break, Zoomies. Yes.
I'm gonna be gone Thursday, so there's no way for me to like take it, the quiz beforehand.
Where are you gonna be?
Disneyland.
No, you'll just have your test score go into your quiz score.
Okay, all right.
Yep.
Sounds good.
All right, here we go. Lights, camera, action. So we've got an illustration and an example, and then we're done. Whew. Wasn't so bad, maybe. So the first illustration is going to illustrate the need for continuity when using the intermediate value theorem. The second example is going to actually be a full, like, hey, here's a function, here's a k value, verify that the conditions are met, and then find the c value that gives you the k value. I probably won't ever tell you that something's 100% going to be on your test, but it is 100% going to be on your test. Okay, you need to know how to do the intermediate value theorem. So pay attention for the next 31 minutes, though I don't think it'll take 31 minutes. We'll see. So illustration 3, we're going to call this because that's what it was called last year. Illustration 3 is going to show our need for continuity for IVT. Oftentimes we shorthand intermediate value theorem as IVT. Cool. We're going to have a piecewise function called f defined on the closed interval from 0 to 3. And its pieces are that x minus 1 is our rule if we're between 0 and 2. And then from 2 to 3, we are the quadratic. So greater than 2, less than or equal to 3. Cool. And the question is oh, dyslexia, sorry. This should be 2 is less than x, which is less than or equal to 3. And the question is there a c in this closed interval from 0 to 3 such that f of c is equal to 2? So 2 is our k value. Again, our k value determines our c value. So one of the things we'll have to do in these problems is to verify that this is an appropriately chosen value of k. In other words, does k fall in between the function values of our endpoints? Well, we need to know what the function values of our endpoints are. So f of 0 is equal to -1. And f of 3, we're now in this piece, is equal to 9. So 2 is definitely between -1 and 9. So it's between f of 0 and f of 3. So that condition of our IVT is met, that we have an appropriately chosen value of k that is actually in between these function values. The issue we have is that we have not met the second condition, which is that the function has to be continuous on that interval, which we're not going to go through the full little eyes right here. We're just going to graph it and see it with our eyeballs. There's a gaping hole in this function at x equals 2. And this function value falls in that gaping hole. So let's graph this out. 2, 3, 4, 5, 6, 7, 8. Actually, I need a little more y here, negative y, so about that. The screen, okay. Thank you. Here's negative 1. And then we need like 1, 2, and 3. So from 0 to 2, we are the line x minus 1, which looks like this guy. Spacing's a little off, why that doesn't look quite like slope of 1. And then bigger than 2, we jump into the quadratic piece. And so as soon as we get bigger than 2, we've jumped up to 4, open circle there. And 3, we're like up at 9. We begin our life as a parabola. Is that thing continuous? Where is it discontinuous? At 2. Figure out what happens. We thought we had a nice k value here, and we do have a nice k value here, because k does indeed fall in between f of 0 and f of 3, because k is 2. The problem and the reason that the IVT fails here is there is this jump here, this lack of continuity, and it doesn't hit those values. In fact, any value bigger than 1 and less than 4 is not getting hit because we have this big jump. So because of the jump, even though k was appropriately chosen and is between f of 0 and f of 3, lack of continuity means there is no value on that interval the interval being from 0 to 3, to produce not just our our k value, but anything between 1 and 4. The lack of continuity screwed us. K was appropriately chosen. If it had been continuous, we would have been golden. So the last example is one in which we will actually be able to verify both conditions of the IVT and then actually find the value C that produces our desired value K. This is it, example 1. We're going to let f of x be 4 plus 3x minus x squared, quadratic guy. And we're going to be considering the interval between 2 and 5. We're going to determine if there is a value call C on the interval from 2 to 5 such that ST, when you plug C in, and actually this should say if there is value or values, you can have multiple values. So f of C equals 1. So before we get too wrapped up trying to figure out what C is, we need to make sure that the conditions are met to make sure that we know that C actually exists. We failed the conditions in this one, so C didn't exist. There was not a C value that was going to produce a function value of 2. So we need to verify both those conditions. Call that A, verify conditions of IVT are met. And you can do this in any order, it doesn't really matter. First, continuity. Well, this is where we kind of just say f of x, you're a polynomial. Therefore, where are we continuous with the polynomial function? All real numbers. Thus continuous everywhere. Well, if something is continuous everywhere, do we think it's continuous on the closed interval between 2 and 5? Yes. Thus continuous on the closed interval from 2 to 5. That wasn't too bad. Second condition. Is our value of k appropriately chosen? Is 1 between f of 2 and f of 5? Well, I don't know. Let's figure out what f of 2 and f of 5 are. F of 2, plug in a 2 for x, 4 plus 3 times 2 minus 2 squared. 4 plus 6 is like 10, minus 4 is like 6. F of 5, 4 plus 3 times 5 minus 5 squared. 4 plus 15 is like 19, minus 25 is like -6. Is is 1 between 6 and -6? Sure is. Somewhere in between there. So because one is between f of 2 and f of 5 and f continuous, we can apply IVT, which guarantees, so we know there exists at least one value of C in that closed interval from 2 to 5, such that f of C is equal to 1. Well, then how do we find C? By attacking this statement right here. Put it on the flip page. It'll be quick. I'll be done. I'm going to chop down your homework quite a bit. Find C. Here's how we do it. We just made the statement or the claim that there's got to be some number C such that f of C is equal to 1. Well, let's replace f of C with what it means. F of x was 4 plus 3x minus x squared. I'm thinking f of C is probably 4 plus 3c minus c squared. And we want to know, when is this equal to 1? This feels like quadratic formula. Woo! Let's rearrange this so that we're equal to 0. I'm going to get c squared minus 3c minus 3 is equal to 0. But you didn't think you'd be doing the quadratic formula when you walked in the door today, did you? Or soap, for that matter. We got all sorts of blasts from the past today. So C then is equal to the opposite of B, which I'm going to call positive 3, plus or minus the square root of B squared, negative 3 squared, minus 4 times A, 1, times C, negative 3, all divided by twice A, which is still 1. Cool. Simplify. We end up with 3 plus or minus the square root. Negative 3 squared is like a positive 9. A negative 4 times a negative 3 is like a positive 12. I'm going to say that turns into like a positive 21. All divided by 2. There's two numbers here. We're claiming that C can either be 3 minus the square root of 21 divided by 2, or C can equal 3 plus square root of 21 divided by 2. But like a quick little check here. And you know what? I'm going to prove that you don't need your calculator every time. I know we're slaves to the calculator, but let's just think about this. What's a rough estimate for the square root of 21? You could just be even more general, somewhere between what two numbers? If you take 3 and you subtract some number between 4 and 5, what type of number do you get in return? And you take that same negative number and divide it by a positive number, what does your number stay? Negative. Is a negative number, whatever it is, going to fall in the interval between positive 2 and positive 5? Not. So this guy fails to be in our interval. Not in the interval between 2 to 5. Gotta make sure we check that. And we could verify this, but we know that if that one's not, this one has to be, because the intermediate value theorem guarantees at least one number in that interval. There's only one left. And since we're careful calculus students, we're going to verify, though, that if we actually plug this in, verify that 4 plus 3 times 3 plus the square root of 21 divided by 2 minus 3 plus the square root of 21 divided by 2 squared actually equals 1. Well, not the nicest thing to plug into a calculator, but you can do it. 4 plus, I'm going to do 3 times parentheses. I want 2 parentheses because I'm going to do 3 plus second square root 21. Close the numerator parentheses, divide by 3. Close the parentheses that hold that whole quotient. And then I need to subtract that whole guy squared, which is kind of dicey. I'm gonna do open parentheses. And I'm gonna do another open parentheses for the numerator, 3, yeah. Divide by 2, thank you. And then we're gonna do 3 plus the square root of 21. Again, close out parentheses, divide by 2, close the parenthesis there, and square it. And if we feel confident in all of our parentheses and everything, we press enter, it should be 1. Quick prayer to the calculus gods. Woo! Look at that. It worked. It gave us 1. We feel good about that value. Whew. So therefore, C equal to 3 plus the square root of 21 divided by 2 is the promised C value as promised by the IVT. What I need you to do for homework is not the entirety of what is written on the assignment sheet. In fact, it's quite a bit less. You're welcome. Here's what I need you to do. And have a softie. I'm not going to make the sub like your homework on Thursday. This will not technically be due till Monday. But there's a good chance I might leave you something to do on Thursday that is also going to be Monday. So choose accordingly. So 1.9. I'm going to tell you the ones that you need to do. You need to do numbers 1 and 3. You need to do $25. And then you need to do 35, 37, 39, and 43. You need to do 1, 3, 29, sorry, 25. Now 29. And then 35, 37, 39, and 43. On the week after this, on Monday, we'll start 110. Probably finish it on Tuesday. Thursday, we will do delta epsilon proofs. And we are shooting for the following Thursday to take our chapter 1 test. That?
Yeah.
No value.
Organs and their function.
Yeah.
Yeah.
Well, so I think it's more, I think it's not more, it's like,
No, I know, it's just.
yeah.
But it's like pretty. No, I
We
did.
did, it's a lot of stuff. Did you guys read chapter 1? Yeah.
I read it in the.
Oh,
I'm just a little stressed.
You know, I would think like, so are you the person that asked about the next? Hey, brother, I have this kind of like stick up his butt math teacher, and he's not super keen on me walking in for 10 minutes. I try my best to.
Try harder.
Oh man, got a bunch of dead space now.